Let's imagine for a moment that we have a digital storage device that is capable of storing decimal numbers. We may imagine further that this device is made of slots, where each slot can take 10 possible states that collectively represent the numbers 0 to 9. In other words, each slot is a decimal digit. Now let's say we have two decimal numbers, a and b, and let's give them some random values. We want to store those two numbers on our device, and we want to optimize our size and memory. To do this, we can write each number in scientific notation. Now we can allocate 10 slots for each number. We can use 2 slots to write down the exponent, then we can use the rest to write the digits. Note that if we had more than 8 non-zero digits, we could only store the 8 most significant digits as the rest wouldn't fit. This is an efficient method of storing numbers of any order of magnitude. Given our slot count of 10 and our 2 exponent slots, we can write down an approximation of any decimal number smaller or equal to this one, accurate to 8 significant digits. And of course, increasing the slot count will allow us to store even larger numbers with even greater precision. Now that we know of a good method to store numbers, we can mirror this in binary. First we write our number, then we convert it to binary, then in scientific notation. Then we store the exponent and the significant digits. A small optimization that we can add is to not store the first digit. As we're working in binary, the highest significance digit must be non-zero, as that is what it means for the number to be written in scientific notation. But in binary, the digit can only be 1 or 0, so it's always 1. Therefore, it is redundant and we can save 1 bit by not storing it. Finally, we have to decide our slot count. The standard is to use 32 total bits. 1 bit dedicated to the sign to store negative and positive numbers, 8 bits dedicated to the exponent, and 23 bits dedicated to the significant digits, which is called the mantissa or the significant. This kind of number is known as the IEEE 754 32 bits floating point number, and it is the most common way of storing numbers on modern computers. Before we can discuss truncation in operations, we need to establish the significance of each bit. Let's write an example number. First, let's label each mantissa bit by its position. Then let's add the exponent to each label. This gives us the true significance of each bit of the number. Let's consider another example number. If we were to add those two numbers, each two bits of the same significance would get added to each other, and the carry bit, if present, is added to the bit of one higher significance. However, because we can only store 24 significant bits, any bits in the second number whose significance is below -4, which is to say the significance of the least significant bit in the first number, any bits of such a significance will be truncated and will not make it to the result, which is a loss of precision in the operation. Finally, let's consider the limit of this truncation by adjusting the exponents of our two numbers, such that they become more than 23 orders of magnitude apart. The significance of the most significant bit of the second number is 3, which is lower than the significance of the least significant bit of the first number. This means if we were to add those two numbers together and store the result, we would get the first number back because the rest of the bits would be truncated. In other words, adding the second number to the first one is effectively the same as adding 0. Such that they become more than 23.